everybody, and welcome to our last video in Unit 4, which will be a continuation of redox reactions, but we are actually going to take redox reactions a step further, and we are going to learn how to balance redox reactions. Now you might be thinking, well, what the heck? Can't we just balance these redox reactions like we've already balanced chemical equations before? And the answer is sort of. In fact, half redox reactions are going to be some of the most difficult reactions to balance. And that's because not only do we have to look at the number and types of atoms on each side, but we also have to make sure the charge is balanced on both sides. And that tends to be a little difficult, especially with more complex problems. So to balance redox reactions, to make it a little bit easier, chemists will often use the half reaction method. Half reaction method. And if you think about a redox reaction, right? Redox reaction has two parts. We have an oxidation part, and we also have a reduction part. So we take the oxidation reaction, which is half of the redox reaction, and then we take the reduction reaction, which is the other half of that redox reaction. We separate them and we balance them that way because it makes it a heck of a lot easier to balance reactions using this particular method. So what is a half reaction? Let's go ahead and get this down here. So a half reaction is either the oxidation or reduction reaction component of or in a redox reaction. So a half reaction is just either the oxidation portion of a redox reaction or the reduction reaction. And we could separate those two reactions given a regular old redox reaction, which we're going to do. Now, you might be like, holy moly, look at these steps to balance simple redox reactions. It's a lot easier to do these, especially the simple ones. We're going to start off with simple. It's a lot easier to do these than it is to talk about how to do them. So the steps are kind of lengthy only because it takes a lot of words to describe what we're doing, not necessarily that this particular method is difficult. So we're doing simple redox reactions here, and that's a key word. So let's go ahead and circle the word simple. To be honest, College Board will not assess you on the acidic solutions or basic solutions. I like to do that though, because if you can do the more difficult ones, you could do the simple redox reactions. Plus I have a great lab that you're going to do a redox titration, and you'll have to balance a reaction in acidic solution. So anyway, I'm getting ahead of myself. Let's go ahead and use these steps and solve sample problem 8 together. So it says, balance the following equation using the half reaction method. Yes, I know you can balance that very easily just by looking at how many of each type of atom is there, but we are going to break this down and do this using the half reaction method first. So step 1 says to determine the spectator ions and write the net ionic equation. So you don't have to always write that full molecular equation to figure out the spectators, because I could see that it looks like I have 2 chloride ions that dissociate here. And it looks like I have some chloride ions here that also dissociate. So even though they're not the same number on each side, we're just going to eliminate those because my chloride ion is going to be a spectator anyway. It's not involved in the reaction. So we know that Cl is a spectator. So I'm just going to eliminate that in my reaction first. I'm just going to write the net ionic equation. So I have Cu plus 2 reacts with aluminum. And I'm not writing states of matter. College Board actually doesn't care if you write states of matter, so that means I don't care. And I have this. right here. So step 1 is done. Although the number and type of element is the same on both sides, so I have one aluminum atom on both sides, and I also have one copper atom on both sides, the charge is not the same on both sides. So I have a +2 charge on my reactant side, but I have a +3 charge on my product side. So I have to take that into consideration. This particular equation is not balanced as it's written. So let's determine what's being oxidized and what's being reduced. All right, oxygen, copper looks like it's going from a +2 charge to a neutral charge, so it must be gaining electrons. This particular reaction, copper +2 to copper, is getting reduced. So I'm going to separate that out. So I'm actually combining steps 2 and 3 here. Going from copper +2 to just regular old copper is our reduction reaction. I'm going to write reduction kind of far off to the left here because I'm going to have to add some other stuff here, which you'll see. So there's my reduction reaction, and therefore aluminum must be my oxidation. So I have aluminum with an oxidation number of 0, going to aluminum with an oxidation number of +3. So this is my oxidation. Al is going to Al +3. So those are my 2 half reactions, right? One of those specifically is showing the reduction, and the other one is showing the oxidation. So I just finished steps 2 and 3 here also. So 1, 2, and 3 are done. Add the appropriate number of electrons to the more positive side of each reaction. Let me scroll down here a little bit. So in my reduction reaction, I have copper +2 that's gaining electrons to become copper, right? In this case, copper +2 must be gaining 2 electrons, right? Because if this has a charge of +2, it has to gain 2 electrons to have an oxidation number of 0. So in this case, we could see that copper is gaining, via reduction, 2 electrons to become elemental copper. Whereas aluminum, I have aluminum with an oxidation number of 0, and this is losing 3 electrons. So if aluminum is losing 3 electrons to become the aluminum cation, looks like it has to lose 3. So +3 electrons are going to come out of that as well. So I'm using these electrons to balance these half reactions. So I'm making sure that the charge is equal on both sides. So 3 negatively charged electrons plus oxidation number of +3 gives me a neutral charge. And the same thing goes for here. So that's done. The only thing is, how could copper gain 2 electrons and aluminum lose 3, right? I can't just have electrons floating around somewhere in this solution. The electrons have to go somewhere. So in order to balance this equation, I have to multiply each half reaction by some number so that my number of electrons is equal on both sides. So if copper is gaining 2 electrons and aluminum is losing 3 electrons, I have to get them to be the same value on both sides. So least common multiple of 2 and 3 is 6. So I want to get 6 electrons in each reaction here. So what I'm going to do is I'm going to multiply all of my values in this reduction reaction by 3. Multiply everything by 3, because that'll give me 6 electrons. To get 6 electrons in my oxidation, I'm going to multiply everything by 2, right? Because then 2 times 3 gives me 6. So that step is done. Let's go ahead and write the whole entire equation out on this time. So we have to make sure we have what's on each side of the arrow. So I'm going to put my arrow here. And let's look at the reactant side first. 3 times 2 electrons gives me 6 electrons from the reduction. Plus I have 3 copper ions. Now my other reactant in this case is my 2 aluminums. Okay, so I'm combining these two reactions now once I did this. Now let's do the same thing for my product side. So I have 3 copper atoms plus 2 aluminum ions plus 6 electrons. Now what we do is we can simplify, just like we did with a net ionic equation. Whatever is the same on both sides then cancels out. So let's use a different color here. And it looks like I have 6 electrons here, and I have 6 electrons there. No matter what, your electrons have to cancel out, right? You can't have some random electrons in the reactant side, nor can you have random electrons in the product side. You have to have an equal number of electrons to show that the appropriate number of electrons is getting transferred. So once I simplify by canceling those species out, I can rewrite whatever's left over. So my final balanced reaction is this. Oops. And if I notice, not only do the number of atoms balance out on both sides, I also have the charge that balances out on both sides. So 3 groups of +2 gives me +6. 2 groups of +3 also gives me +6. So this equation is now balanced. Little bit tedious, right? Especially for an equation like this. It's very simple to look at this equation. However, this is the simple method, right? So in order to do the more complex problems, we have to understand this, this simple method here. So let's go ahead and use this to do something slightly more complex, okay? So again, lots of steps here. Doesn't necessarily mean that it's super difficult. Just, takes a lot of words to explain how to do it. So let's keep this up here and we'll do the steps along with sample problem 9. Balance the following redox reaction, assuming it occurs in acidic solution. So let's look at step 1. Assign oxidation numbers to all elements, to determine what's getting oxidized and reduced. Iron here has got a charge of +2. Oxygen's always -2. This must mean manganese is going to be +7. Here, iron is +3, and here manganese is +2. You might be like, holy moly, Mrs. Snyder, now I see what you mean, because how do I have oxygens in my reactant side and not in the product side, right? This is how we balance something like this. Okay, it gets a little bit trickier. Looks like iron is being oxidized, so it's losing an electron, whereas manganese is getting reduced. It's going from a +7 charge to a +2 charge. So let's go ahead and separate these two half reactions here. Oxidation we said is iron, going from iron +2 to iron +3. And my reduction is permanganate to that guy right there. So assign oxidation numbers, did that. We separated the two half reactions. Balance the elements in the following order. So it says all elements except for oxygen and hydrogen. Let's just look at this oxidation first. This one's a little bit easier. So iron's balanced, so I don't have to worry about that. Balance oxygen. Well, I have no oxygen, so we're good. And I also don't have hydrogen, so I don't have to balance that one. Balance the charge by adding electrons to the more positive side. So oxidation, oil rig, oxidation is a loss. I should have electrons on my product side. And to get these charges to equal, looks like I have to have 1 electron that comes off of this. Okay, you're always adding electrons to the more positive side of the reaction. That one's done. That's a nice and easy one. Let's take a look at this reduction reaction, though. In fact, I think I'm going to have to just erase that for now, because I'm going to have to add a little bit more stuff there. So let's balance this one. Balance all elements in the following order. Okay, all elements except for oxygen and hydrogen. Manganese is already balanced, so I don't have to worry about that. Balance oxygen by adding water molecules to the side with less oxygen atoms. So I do have 4 oxygen atoms in my reactant side, but I have none in my product side, which means I have to add 4 water molecules to get those oxygen atoms to balance out. So now I have 4 oxygens here, and now I have 4 oxygens here. So this works out. A is done. Oh, A and B are done. Now let's balance hydrogen by adding hydrogen ions to the side with less hydrogen atoms. We already said that something that's acidic is a source of protons. So because this is in an acidic solution, we're going to add protons to this. So, all right, I have no protons in my reactant side, and I have 8 protons in my product side. So it looks like I have to add 8 to my reactant side to get those to balance as well. So that one's done. So at this point, the number and type of elements are balanced, but the charge is not balanced. So balance the charge by adding electrons to the more positive side. Let's scroll down here a little bit. Here, my product side, I have an overall charge of +2. Okay. Whereas here, I have 8 plus -1. I have an overall charge of +7. So I have +7 to +2, right? We know this is a reduction reaction. I could write this over here. So reduction is a gain, oil rig, right? I know I have to be gaining electrons. So there's going to be electrons on the left side of my reaction here. If I have a +7 going from a +2, I would have to add 5 electrons, okay? Because 5 negative things plus 8 positive things gives me a charge of +3. -1 is +2, which equals the +2 from manganese. However, now what you have to do, that one's done, multiply each half reaction by an integer, right? Because we need the number of electrons to be the same in both the oxidation and the reduction. Looks like I have 5 electrons being gained in the reduction, but I have 1 being lost in the oxidation. So I have to multiply everything in that first equation by 5. And that one's done. So now let's combine the two. So I'm going to try to put the arrow somewhere over here so I can add everything. Let's start off here. So I have 5 Fe+2s. Plus, now I could go to the reactants in my reduction reaction. So I have 5 electrons plus 8 protons plus a manganese ion, or not manganese, permanganate. Now let's do my product side. So 5 Fe+3s, 5 electrons. Then I have the manganese ion plus 4 water molecules. And now what I can do is, so combine the half reactions to get a single reaction. Then it says simplify by canceling out the species that appear on both sides. And remember, you cannot have any electrons in that last reaction. Here I have 5 Fe+2s, but here I have 5 Fe+3s. This and this are not the same species. They have 2 different oxidation numbers, so they do not cancel. What does cancel in this case are only your electrons, which is how it should be. Electrons always have to cancel. Sometimes you might have some other cancellations along the way, but in this case, we don't have anything extra. So then we'll just rewrite whatever's left. I have 5 Fe+2 plus my 8 protons plus a permanganate ion, 5 irons with a +3 charge, a manganese ion, and 4 water molecules. And that's how to balance a half reaction in an acidic solution. Why is it acidic? Because I have protons in my reactants. And as we know, protons are what makes something acidic. Now, what happens if we have a basic solution? Okay, steps look easier. Steps are shorter. Doesn't mean it's actually an easier problem. But we actually have to add on to the last one. So you'll notice step 1 says balance the reaction as you would for an acidic solution. So we're going to balance this the same exact way, and then we'll pick up with step 2. Let's assign some oxidation numbers. So oxygen's -2. This is a peroxide, actually. So peroxide's -1. Hydrogen's always +1. Chromium here, this is -14, right? -2, which means that this has to be +12, but there's 2 of them. So it's +6. This chromium is +3. This oxygen is 0. Sorry, this doesn't look very good. Hopefully you can hear me say that so you get them all correct. Let's see. Looks like oxygen is actually getting oxidized in this case. So oxygen is losing an electron. We're going from oxygen with a -1 charge to oxygen with a 0 charge. Yes, there is oxygen in this example as well, but we're actually going to use the other species in this case, just because it's going to make our life a little bit easier. So oxygen's getting oxidized, whereas chromium is getting reduced. It's actually gaining 3 electrons there. So let's do our reduction, which is, let's see, do it over here. Make sure I have enough space. The dichromate ion going to chromium +3. And I have my oxidation, which is peroxide, going to oxygen. Let's start off with this one. This one's a little bit easier to do first. So oxygen is already balanced. I don't have anything else to add. Looks like all I have to do is add some protons. So I have 2 protons in my reactant side. Looks like I need 2 in the product side. And that affects my overall charge. So I have an overall charge of +2 here. Charge is neutral on my reactant side. Looks like I'm going to lose 2 electrons there. Remember, oxidation is a loss of electrons. So for your oxidation reactions, you should have electrons on the product side because it's losing electrons. Your reduction reaction should have your electrons on the reactant side because it's gaining those electrons. Balance everything other than oxygen, hydrogen. In this case, I do have 2 chromiums in my reactants, and I gotta have 2 here. Balance chromium first. Let's balance oxygen. Looks like I got 7 here, so I'm gonna add 7 water molecules. Now let's balance hydrogens. Looks like that gives me 14 in my product side. I have to have 14 in my reactant side. And then we have to make sure our charge is balanced. So looks like I have 14 -2. I have an overall charge of +12 on my reactant side. And here I have an overall charge of +6. So I have 2 groups of +3 gives me +6 is neutral. So to go from +12 to +6, I have to add 6 negatively charged electrons. There's our reduction half reaction, and here's our oxidation half reaction. To get these to be the same, I got to make sure my electrons are the same. So I have 6 and 2. Let's just times this bottom one by 3. So I get 6 on both sides. Almost done. So let's go ahead and write what's on both sides. I have 6 electrons plus the 14 protons plus the dichromate plus, looks like I have 3 peroxides. Now let's do all of my product side. I have 2 chromium ions, 7 water molecules, Oh, what the heck? Looks like I have 3 oxygen molecules, 6 protons, and 6 electrons. All right, we got a little bit more than just electrons to cancel out here. So let's identify what's the same on both sides. Looks like I do have my 6 electrons, so that's good. However, I do have protons that are present on both sides. Here I have 14 protons, and here I have 6. So 6 of these protons gets totally canceled out, and 14 minus 6 gives me 8. So we're simplifying this overall reaction, and you can do that, just simplifying. Notice we're not even at the basic side yet. We're still just balancing this as if it was an acidic solution. So let's write the simplified version out. I always feel super smart when I do these. I'm like, look at me go. Yes. Okay. All right. Step 1 is done. That was all step 1, balancing it as if it's an acidic solution. Step 2 says add an equal number of hydroxide ions as protons to one side of the equation to form water molecules. So, and it does not say to one side, this should actually say to both sides, change this to both sides of the equation. So I have 8 protons, right? But if this isn't a basic solution, I'm not going to have any protons, right? So I have to get rid of these somehow. And the best way to get rid of them is to add 8 hydroxides, because 8 protons plus 8 hydroxides is going to give me water molecules, right? But whatever I do to one side, I have to do to the other side. So I'm going to add 8 hydroxides there as well. This cancels out. Well, doesn't cancel out, but that's going to give me, let's rewrite this. Go down here. I have 8 water molecules plus the dichromate plus the peroxides yields 2 chromium ions plus 7 water molecules plus 3 oxygens plus 8 hydroxides. Guess what? You're still not done, because what happened is now you have water molecules on both sides, right? I have 8 water molecules in my reactants and 7 in my products. Let's cancel those out, right? Don't have anything extra that you don't need. This is unnecessary, and this 8 turns into a 1. So now, finally, we should be done. Let's rewrite this overall equation. 1 water molecule plus the dichromate ion plus 3 peroxide molecules yields 2 chromium ions, 3 oxygen molecules, and 8 hydroxide ions. Holy moly. There it is. This is chemistry, right? Like, you've been doing chemistry, but like, this is it. This gets me excited because it's like, this is tedious. And when I do these, I get very frustrated when I make a little mistake. So like, I get it because I still make mistakes, but you have to take these slowly. You have to follow the steps. Okay. Follow those steps. Be very careful. Take your time. Like I said, College Board for your AP exam, you don't need to know this, how to do this, and you don't need to know how to do this. What you need to know are these simple equations. But if you can do those hard ones, you should definitely be able to do the easy ones. So we're not going to like press on with those more difficult ones, but I wanted to show you that because there is a lot of really cool labs we can do with the redox reactions with acidic and basic solutions. And I wanted you to see that so that way when we do the one lab and if we come across any other ones that you know or that you have at least seen how to balance more very complex half reactions. Hopefully your brain is okay. I know that was a lot of information, lots and lots of chemistry. So as always, if you have any questions, please let me know. We will practice this in class, right? I got a couple of things that we're going to do. And otherwise, I will see you in our next unit, which we're actually going to skip to equilibrium. So I will see you in unit 7, all about equilibrium. Bye.